So in today's lesson, the last section before that we need to do to finish the course, we're going to look at how we can carry out a hypothesis test for a normal distribution. So we're going to imagine we have 10 children, one of each age between 0 and 9. So here is our population. Our population in this case is the age of our 10 children who are aged between 0 and 9. So if we want to work out the mean of this population, the mean of our population here is 4.5 years, 4.5 years. So this is called our population mean. Now, suppose we want to take a sample of 4 children. So in our first sample here, we've got 4 children with ages 1, 3, 7 and 8. And the population of this particular sample is 4.75. If we take a second sample here, the ages of our children are 6, 2, 0 and 9. The mean of this particular sample is 4.25. Now, we can see here that 4.75 is quite close to our true population, but for each sample we get, the mean of each sample is going to vary slightly. We might have another sample. We might have a sample with ages 0, 1, 2 and 3. Work out the mean of that, which is 6 over 4. And which would give us a mean of 1.5, which would be down here somewhere. Now, if we take lots and lots of samples here, what we're finding, and we work out the mean of each one, what we find is that the mean of the samples are close or are distributed normally or follow a normal distribution. So if we then take 1,000 random samples, as we said here, it falls close to a normal distribution. And what we've got to remember as well is that in the histogram, we've got to remember our continuity correction here. So in our histogram, 5 actually means the sample mean is greater or equal to 4.5 but less than 5. So the question we're going to ask is, what sort of distribution does our sample mean follow? So if we look from left to right here, it does seem as though it is approximately normally distributed. So it's got a rough bell-shaped curve and is symmetrical about the mean. So we know that the population mean mu is 4.5. So on average, what sample mean do we see? Well, we can see here that it is symmetrical about the mean. So therefore we can say that the sample mean x bar varies around the population mean mu, but on average is 4.5. The next question we ask ourselves is the variance of our distribution of the sample means the same as the variance of the population of the children? And if we look here at this distribution, we've taken a sample size of 10 children, and here we had 1,000 samples, but the sample size was 4, then we can see that the spread around the mean is different in both distributions. So no, the variance isn't the same in our normal distribution and the distribution of the sample means, and the variance depends on the sample size. So if the sample size is small, the sample means are likely to vary quite a bit, as we can see in this example one, graph 1 at the top. But with a larger sample size, so as in this graph here, the second one, where our sample size was 10, we expect the different mean to be closer to the population mean, but the variance is the spread of the data. The data is all closer to the mean. So therefore, for a random sample size n, so for a random sample size n, taken from a random variable x, what we can say, the sample mean is normally distributed with a mean mu, same as the population mean, but with a variance of sigma squared over n, and remembering that n is our sample size. So in this example here, taken from your textbook, it says a certain company sells fruit juice in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3 millimeters. The company claims that the mean amount of juice per carton, mu, is 60 millilitres. So what we have here, we're going to say we've got a random variable x, which can be modelled on a normal distribution with a mean mu, which is 60, and with a standard deviation of 3 millilitres. A trading inspector has received complaints that the company is overstating the mean amount of juice per carton and wishes to investigate this complaint. The trading inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1 millilitres. Using a 5% level of significance and stating your hypotheses clearly, test whether or not there is evidence to uphold this complaint. So therefore, what we can do is we can say therefore our sample mean can be modelled on the normal distribution with the mean the same as the population mean, and the variance will be 3 squared over the sample size, which is 16, because it's taken a random sample of 16 cartons. And we can write this as, just simplifying our fraction, it would give us a mean of 60 and a variance of 0.75 squared. So we've got to state our hypotheses. So if the inspector has received complaints that the company is overstating the mean amount of juice per carton, therefore our null hypothesis, H0, is going to be that the mean is actually equal to 60, and our alternative hypothesis is that the mean is going to be less than 60. Right, so We therefore want to work out the probability that our sample mean is less than 59.1. Okay, and we're testing at the 5% level of significance. So what we have here, if we just always draw a little diagram, it does help. A bit shaky here, but never mind. So we have our 60 and we have our 59.1, and we've got a one-tailed test, and we're testing at the 5% level of significance. So we have probability of falls area 0.05. And what you've got to remember, if it falls in this region here, we would reject the null hypothesis, so that would be a reject. And if it fell here, we would accept. The null hypothesis. So using our calculators, we can work out the probability that our sample means is less than 59.1. We can work that probability out using our calculator and using the normal CD button and inputting a mean of 60 and a standard deviation of 0.75. Remember here, that is the variance, so in the calculator, the standard deviation would just be 0.75. So if we use our normal CD button, this probability is 0.1151. Now, therefore, because it would fall in this region here, in other words, because 0.1151 is greater than 0.05, what we say, there is insufficient evidence to reject the null hypothesis. So what we can say, therefore, because of this, because the probability that the sample mean is less than 59.1 is 0.1151, which is greater than our 0.05, testing at the 5% level of significance. Therefore, and it falls in this area here, therefore we can say there is insufficient evidence to reject the null hypothesis. And what's really important at this stage is always refer your conclusion to the original question. Okay, so this therefore tells us that there is not a significant difference between the population mean and the sample mean. So what we're going to look at next is finding a critical region or critical value. So for a hypothesis test for the mean of a normal distribution, we need to standardise this test statistic. So for a sample mean of a normally distributed random variable, so sample mean x is normally distributed with a mean mu and variance sigma squared over n. Then z equals the sample mean value minus the mean over sigma divided by root n, which is normally distributed random variable with z being a standardised normal statistic, with z modelled on a normal distribution with a mean of 0 and a standard deviation 1 or variance 1 squared. So in this example, we're told that a machine produces bolts of diameter d, where d has a normal distribution with a mean of 0.58 centimetres and a standard deviation of 0.015 centimetres. The machine is serviced, and after the service a random sample of 50 bolts is from the next production run is taken to see if the mean of the diameter of the bolts has changed from 0.58. The distribution of the diameters of the bolts after the service is still normal with a standard deviation of 0.015 centimetres. So here in the first part of the question we're asked to find at the 1% level the critical region for the test, stating the hypotheses clearly. Now we can see here, this section here, it says that a sample of 50 bolts taken from the next production run is taken to see if the mean of the diameter has changed from 0.58. So in other words, is not equal to that, and that implies, or that means therefore, that we are going to have to do a two-tailed test. And if we're testing at the 1% level, each end of the tail will have a probability of 0.005. So we've been asked to find whether the population mean differs from 0.58. So we have a two-tailed test. So we're going to have a null hypothesis. So our null hypothesis, 0, will be that the mean equals 0.58, and our alternative hypothesis will be that the mean is not equal to 0.58. So if we assume the null hypothesis, so if the mean is equal to 0.58, that means the diameter of the bolts will be modelled on a normal distribution with a mean of 0.58 and a standard deviation here of 0.015. And remember, that means it's inside the bracket 0.015 squared. And this is our population distribution, assuming that the null hypothesis is true. So the distribution of the sample means, therefore, will be of sample size 50 will have the same population mean 0.58, and the standard deviation will be 0.015 over the square root of 50, but inside the brackets for the normal distribution we have the variance, so it's 0.015 squared as in the top, but we divide by the sample size n, which in this case we're told is 50. Now, because we want to find a critical region, we want to standardise our distribution for the sample mean. So that means, using the coding, we will have that Z will equal D minus the population mean divided by the standard deviation for the sample distribution, so sigma over root n. Okay, so using that coding we can then standardise it, and then using the standard normal distribution we can then work out what our critical region is using the percentage points or using the calculator. So if we input our values then, so following this we can therefore say that Z equals the distribution for the sample mean D minus the population mean, which we know, so I can, instead of that, I can actually put 0.58 and divided by 0.15 over root 50. So if I've drawn here, I've drawn my standard normal with a mean of 0 and a standard deviation of 1, and we want to work out the probability that our value lies in this region here. So to do that, I can either use this table here to find it, which is this value here. That would give me my Z value, or I can use the calculator using an area of 0.05, a mean of 0 and a standard deviation of 1. This gives me my two values, so I have minus 2.5758. Because it's symmetrical, this end here is 2.5758. Now substituting this value into this formula here for my Z value, I can therefore work out my value for D. So this would give me minus 2.5758 equals D minus 0.58 all divided by 0.015 over root 50. And if I rearrange that, I will get my value for D to be 0.5745. So if we just recap here, so what I've got here is I've got my standard normal, Z distribution with a mean of 0, standard deviation of 1. I've worked out my first Z value, so we're doing a two-tailed test at the 1% level, so 5% here. So what I've found so far, my first Z value is minus 2.5758 and the upper tail 2.5758, the positive, so we've got plus and minus 2.5758. And using the formula, I've subbed in my minus 25758 for my Z, and I've then subbed in the mean of 0.58 and divided by the standard deviation 0.015 over root 50, which has given me my first p-value 0.5745. I'm now going to do the same for the positive Z value, which will I then sub into the formula, which will give me the upper limit. So that will give me 2.5758 multiplied by 0.15 over, multiplied by 0. Just rearranging the formula, this is 0.015 over root 50, and then it was minus mean, so I'm going to plus 0, I'm going to add 0.58, and that will give me my other value here. So when I work that out, I get 0.584. So D equals 0.5854, which gives me this value here. So that's that value there. Okay, so now I know that my critical region, so the critical region is where D is less than 0.575, which gives us this region here, and the other critical region is where D is greater than 0.585. So finally, to answer the second part of the question, it says the mean diameter of the sample of 50 bolts is calculated to be 0.587. So comment on this observation. Now, our original hypotheses were, the null hypothesis was the mean was equal to 0.58, and the alternative was that it wasn't equal to 0.58. And our critical region, if we were to reject our null hypothesis, D, mean diameter would have to be, of the sample, would have to be less than 0.5745 or greater than 0.5854. Now the mean we've got here, the mean diameter of a sample of 50 bolts here, we've been told, is 0.587. And this falls inside the critical region. So it would lie here. 0.587, 0.587. So 0.587 lies in the critical region. So what that therefore means is that there is sufficient evidence at the 1% level to at the 1% level that the mean diameter has changed. So in other words, we can reject the null hypothesis. But again, you must always relate your final conclusion, your observation, to the original question. I know I've used this, the Z value, but as you know, I wanted to go through that because I think it's good practice to know how to do that. We could have avoided all this and just used our calculators to work out these values here. So I will, on the next page, I will just explain how to do that. So to work out these values directly, all I need to do is in the calculator, I need to work out, remember when using the calculator, you've got to remember the inequality is less than, so the probability D is less than. So what we actually want is the probability D is less than D equals 0.005. So if I use a mean of 0.58 in my calculator and a standard deviation of 0.015 over root 50, then I will get my D value, and I make the area equal to 0.005. My value will be equal to 0. It will be equal to 0.5745. And then so that's using that critical region there. To work out this value here, I'll do it in green, to work out this value here, this probability it's less than, then we want it equal to 0 probability that it is less than 0.995. That would be our area, so that's what we'd put as our area into the calculator. Okay, using the inverse normal button. And again, we would input our values here for the mean and the standard deviation, which will give us our second, the upper bound for our critical region to be 0.5854. So probably quicker and easier to use the calculator, but remember the inequality, so we need it less than when using inverse normal. Using the calculator. And there's no reason why you shouldn't use the calculator. You've just got to remember these little things which could throw you, which could mess up your whole answer. So remember, calculator is less than. You can use the coding formula, so you can work out your Z values, put those in, and remember, if using the percentage points table, the inequality is greater than. But to be honest, I think you're probably going to stick with using the calculator. Now, as far as I'm concerned, we have covered all the course, and I've covered all you need to do for the statistics course. So here we're told that Roasters coffee is sold in packets with a stated weight of 250 grams. A supermarket manager claims that the mean weight of the packets is less than the stated weight. She weighs a random sample of 90 packets from their stock and finds that the weights have a mean of 248 grams and a standard deviation of 5.4. Using the 5% level of significance, test whether or not the manager's claim is justified. State your hypotheses clearly. So we've obviously got a one-tailed test here. So our null hypothesis is that the mean weight is 250 grams, and our alternative hypothesis is that the mean weight of the packets is less than the stated weight over there. So we're told that it's less than the stated weight. So the mean is less than 250. So we've got a one-tailed test, and we've got a mean here of 250. Testing at the 5% level of significance. Okay, and so we need to work out what that critical value is. So if we're testing it, so she then takes a random sample of 90 packets and finds her weight. So we've got a random sample. The mean of that random sample is going to be 250, and the standard deviation is going to be 5.4, so inside we'll have 5.4 squared over n, which is 90. Right, so using our calculator, we can work out what our critical value is. So you get the menu button, we want it's less than, so we're going to work out what that is. So if I put the value, so our area is 0.05. The standard deviation is going to be 5.4 over root 90, and the mean is 250. And that would give us a critical value of 249. Right, so testing at the 5% level of significance, she said her mean weight was 248 in her sample. So a sample had a mean weight of 248 grams and a standard deviation of 5.4. So testing at the 5% level of significance, we can see that 248 is in the critical region. So we can say that there is sufficient evidence to reject the null hypothesis, and therefore the manager's claim is justified. So again, referring to the context of the question again. Here's a nice little question. It helps if you draw a diagram. So if we check this little bit out here, it says the time x minutes taken to fly from London to another city has a normal distribution with a mean mu minutes. Okay, so we've got a mean there, mu minutes. Right. It says, given that the probability that x is less than mu minus 15 equals 0.5 equals 0.35, so that area there, 0.35, and this here is mu minus 15. Find the probability that x is greater than mu plus 15, given that x is greater than mu minus 15. Okay, so we need that. Right, so what we can say here, so what we're actually asked to find is the probability that x is greater than mu plus 15, given that x is greater than mu minus 15. So using our conditional probability rule, that means what we have on the bottom of our fraction is that. So that's the probability that x is greater than mu minus 15. And on top, we're going to have the probability that x is greater than mu plus 15. Now what you've got to remember, what goes on top is the intersection of our A and B. So if you think about this sensibly, as it says here, little tip in the box here, the intersection above mu plus 15 and mu minus 15 is just this area here. So that is our intersection. So that is what goes on top there. Now working these out, we are told that the probability that x is less than, x is greater, probability that x is greater than mu minus 15. So if this probability over here in yellow, if that's 0.35, then the probability it's greater is going to be 1 minus 0.35, which is 0.75. 0.65. And the probability that it's greater than mu plus 15 is going to be 0.35. If you think about the symmetry of the graphs here. So that little area is also 0.35. And working that out will give us our probability, which is 7 over. So reading this question again, we've got the length of time L hours that a phone will work before it needs charging is normally distributed. So here we've got a normal distribution with a mean of 100 hours and a standard deviation of 15. So we have L modelled on a normal distribution with a mean of 100 and a standard deviation of 15 hours. So there we go. Quick diagram of that there. So mean 100. Right, it says find the probability that L is greater than 127 hours. So we need that area there. Okay, so the probability that L is greater than 127 hours. So think about the probabilities. That is actually, if I'm going to use a calculator, I need the inequality, remember, to be less than. So we can say that's same as 1 minus the probability that L is less than 127. And I can use the normal CD button with a mean of 100, standard deviation of 15. I can have my upper bound is going to be 127 and my lower bound, usually you can take it as being 5 times, at least 5 times the standard deviation below the mean, and in this case I'm going to use my lower bound as 15. So I put in my upper bound as 127, my lower value is 15, I put in my mean as 100, standard deviation 15, and I got 0.9641. So that becomes 1 minus 0.9641, which gives me a probability of 0.0359. Now to answer part B, it says that Alice is about to go on a 6-hour journey. Given that it is 127 hours since Alice last charged her phone, so given that the probability that L is greater than 127, find the probability that the phone will not need charging before her journey is completed. So we have 127 hours plus 6 hours is 133. So what we want for part B at C is the probability that L lasts for more than 133 hours, given that it is 127 hours since her last charge. So if we look at that, that is basically what we need to work out. It's a conditional probability. So we know what our denominator is. The denominator will have the probability that L is greater than 127 hours, which we've worked out up here. And the probability it's greater than 133 hours is, so if you think about it, we want the intersection of these two. So if it lasts more than 127 and more than 133, if it lasts more than 133, it's lasted more than 127. So the intersection there is that the probability that L lasts more than 133 hours. So using the normal CD button again, I can work out the top. So my lower bound is going to be 133. my upper bound is going to be a larger number, at least 5 standard deviations above the mean, and my mean is 100, which we've got up here, and standard deviation I put in as 15, and that will give me the probability that it's greater than 133 using the normal CD button, which I've just said, as being 0.0139 divided by the probability it's more than 127, which I worked out in my previous answer, so 0.0359, which gives me an overall probability of 0.387. And rounding up to 2 decimal places, 0.39. This is quite a tricky question. We've got IQ is distributed as x, a random variable x, with a normal distribution of 100 and a standard deviation of 15. So a person is considered to be pretty smart if their IQ is at least 130. Determine the median IQ of pretty smart people. So we want to know if we've got IQs above 130, we want to know what the median of those people, of those IQs, we want to know what the median IQ of the pretty smart people is. So we're going to say, okay, let A be the median IQ of pretty smart people. Okay, so think about probability. I mean, this would be quite hard to recognise. This is quite a pretty hard question. But what I could say is, okay, the probability that x is greater than A, given that x is greater than 130. So if we're just looking at our pretty smart people, so that's everyone with an IQ of at least 130, so 130 and above, then the median of that is going to be A. The probability of it being A is halfway between those people, is therefore going to be 0.5. So thinking about what we did, think about our last questions therefore. That would be like us saying the probability that x is greater than A over the probability that x is greater than 130 is equal to 0.5. Just rearranging this because we want to work out what A is. The probability that x is greater than A is equal to 0.5 times the probability that x is greater than 130, and which equals 0.5 times 1 minus the probability that x is less than 30. And you can see here we're going to use our normal CD button and the mean here, which is 100, and a standard deviation of 15, and we'll put that into our calculator to work out that value there. Sorry, that should have been 130. So using my calculator, upper bound 130, lower bound I made about 10, mean of 100, standard deviation 15, I get 0.5 times 1 minus 0.9772 and putting that into my calculator, I get 1 minus that multiplied by 0.5, I'll get 0.0114. And that's just using the calculator. So now I've worked out the probability that x is greater than a. So 1 minus the probability that x is less than a equals 0.0114. So the probability that x is less than a equals, just rearranging this, is equal to 1 minus 0.0114, which equals 0.9886. So now we can just use the inverse normal now to work out our A. So we've got our probability, our area here, got our area, and at the top here in the question, again, we use our mean as 100 and standard deviation of 15. So using our inverse normal, so an area of 0.9886, a mean of 100, a standard deviation of 50, will give us our solution, our solution. So it'll tell us what A is equal to. So it gives us this value here. So I can say that doing that, putting it in the inverse normal, A equals 134.15 or 134 to 134.152 or 15. And there we go. And that's quite a tricky question. You've got to recognise that you're going to use the conditional probability and the normal distribution together. So it is quite hard, but I think once you recognise that you've done one or two, it will get you some good marks. I hope that's helped, and any questions, see me. But like I said before, as many questions as you can from 3G, particularly the marked questions, but some of the early ones, I think all questions are slightly different, and you need to have met them all to just ensure that you've covered all the material. And obviously you really should work through as much of the mixed exercise as you can. There are a lot of questions there, I know, but this is a big topic in statistics, and it will come up in lots of different guises, as you've just seen here with probability.